theorem, let A, B, C be non-empty sets, and let function f A maps to the B, and the function g B maps to the C, B functions. If f and g are invertible, then G composition f A maps to the C is invertible, and G composition f inverse is equal with the inverse of f composition inverse of G. So now let's see how we can prove this theorem. And let's go to the next slide. To show that we need to apply the following, in order to prove the theorem, we need to apply the following corollary and the lemma. This corollary says let A and B non-empty sets, and let function f, A maps to the B and GB maps to the A, B functions, of course. Then G is invertible function for f in and only if f composition G is equal to identity of B, and G composition f is identity of A. It means identity of elements with respect to the function f, and this identity is with respect to the function G. And we need to use this lemma, which lemma has these identities. The function f composition with identity A is equal with the identity B, identity of elements B, composition with the f R f. So this is identity. Whatever we multiply with identity, we get itself. And here holds the associative property in the composition. And to prove this theorem here, we need just, in our case, we need just to show, we need to verify those two composition are identity maps. So how we can prove it? Let me take a pen here, and first of all, let's take this first identity map. Let's say we have a G composition F, composition function F. Everything is a composition of the inverse function F and composition function G. So, and this one is going to be identity of elements in the set C. Identity of a set C. So this is C. How we can. Now, because here in this case we are applying the lemma, what we had here, this lemma we are going to apply. And when we apply this lemma, we're going to have a G is a composition, and is composition F, composition F1, in fact the inverse of F, and everything is a composition of a function G, inverse of G. And what happened here? This composition of F in F minus 1 is going to be the identity. This is a composition. Identity of B, of the element B, because the inverse function of F is going to be in the set B. And this is a composition of G, inverse function of G. And what's happening here? This, according to the lemma, the function G composition of identity B is just function G, which is a composition of the inverse function of G, and we already proved this is equal to the identity C. So the first one here holds. Because the first one holds, let me make this is holds. And now let's go and try to see the second identity map. We have here inverse function of f, composition with the inverse function of g is a composition of g, function g composition of function f. Everything is equal with the identity map of element or in the set A. So let's see here, can we prove it? So again, as we did before, f, inverse function of f is composition of inverse function of a g, composition of function g, and everything is composition of function f. So here we are applying the lemma, the elements of lemma we are applying. And now what we are going to have, here we already, let me write this inverse function of f and a composition. So I'm just rewriting, but the composition g, inverse function of g and composition of g according to the lemma here, to this corollary, I'm sorry, is equal with the identity. You see f and g is identity b, or g and f is identity a. But in our case is because we are going from set C to set B, this identity is going to be AB, identity B. And composition function f. And again, we are applying here the lemma, this lemma here, and means but this is inverse function of f. Inverse function of f time AB, or function f time identity b is equal to the f. So we have here f, inverse function of f is a composition of f, because identity b time, identity b composition of f is just a f. And when we have here now this mapping, here this composition from inverse function f to f is going to be the identity in the set A. So this is what it is. And we already proved another second identity map, which means it holds, and this completes the proof of the theorem, of this theorem here.